Hello. In today's talk, I'll present the topic of social choice over large decision spaces. My name is Kamesh Munagala. I'm a professor at Duke University. This work is joint with Brandon Fain, who used to be my student at Duke, but now he's a faculty member at Duke, and Ashish Goel, who's professor at Stanford. This work is a combination of 3 papers, and they are joint with 2 high school students, William Fan and Nina Prabhu, who are now at Yale and Stanford, and Sukol Sakshu Wong, who is Ashish's graduate student at Stanford. Okay, so the application that will motivate a lot of this work is so-called participatory budgeting. In participatory budgeting, residents vote on project proposals to decide how to spend a portion of their city's budget. Participatory budgeting is popular in South America, North America, Europe. It's implemented in, like, I think around 1,000 cities around the world. I have collaborated on an online voting platform for participatory budgeting. This platform is built by Professor Ashish Goel and his students at Stanford. So typical PB election ballot has a bunch of projects that the city wants to build along with the monetary cost of these projects. This is an example of the projects from the city of Boston. One mechanism of voting that has been implemented is what is called Knapsack voting, where given the total budget of the city, in this case $1 million, a voter can choose projects that fit within that budget. So in this case, the voter has selected the first and the third projects, he still has $440,000 left, and he can choose more projects that fit in that budget. The set of chosen projects will form this voter's vote. So this is different from standard voting, and let's understand how it is different. So firstly, the space of alternatives is very large because you can view each budget feasible collection of projects, or every subset of projects that fits within the budget as a possible alternative. That will be the space of alternatives, and the voter is choosing their favorite alternative from that space via the knapsack vote. And it's unreasonable to expect voters to rank all these alternatives. I mean, in the knapsack vote, they output their favorite alternative, but they don't really rank all the alternatives. If we impose some utility over the projects, say additive, and we could have simple up-down voting on projects and pretend that the voters just have additive utility over these projects, but that may miss out complements and substitutes in these projects, right? A voter may not want both the first and the second projects, but individually he might like the first project and the second project. So what can we reasonably expect a voter to do? I mean, we can reasonably expect a voter to output their favorite alternative, as well as compare a few alternatives. Going beyond participatory budgeting, we have been trying to build platforms where voters can actually deliberate in small groups, and that leads to the proposal of new alternatives. In real life, this happens, for example, in participatory budgeting before the voting phase, where participants get together or some members of the city get together and decide what exactly should be put to vote. Right? There are hundreds of projects, but they don't want to put hundreds of projects to vote. And we can build platforms to facilitate this kind of deliberation in small groups. And when you build this kind of platform, a constraint is the number of people who can participate on the platform at once. So what I have shown here is a platform that we are building. It's available at stanforddeliberate.org. And here you can see that there are 8 or so participants who are talking and deliberating about how to do electoral reform with an agenda that is there on the right-hand side. So in this talk, I'll focus on social choice with large outcome spaces. And the question that we ask is, how do we reason about voting schemes in such spaces? In particular, we consider randomized mechanisms that use simple queries, such as favorite query. What is your favorite alternative? And this can be generalized to top K queries that asks voters for their top few favorite alternatives. A comparison query where given 2 alternatives, the voter can be asked which of these 2 alternatives do you prefer. For example, in participatory budgeting, you can show the voter two different budget allocations, like two different subsets of projects, and ask them which subset they would prefer. And the relevant question for large outcome spaces are, how many voters do we need to find a good outcome? Suppose we can't like get the entire city to vote. What sample size of voters do we need to find a good outcome? How many queries do we need to ask per voter, like queries of the favorite or comparison type? And going beyond favorite and comparison queries, are there other queries that do better or that are better motivated by the applications we are looking at? Okay, so that is the high level goal of this talk. So before proceeding further, let's look at the analytical framework that we will work under. And since this is a distortion workshop, the analytic framework will be distortion. So we will work in the framework of implicit utilitarian voting, where we assume that voters have hidden cardinal preferences, which are utilities or costs over alternatives. And the metric of performance of a voting rule will be its comparative ratio with respect to the social welfare, which is the sum of the costs for the different voters. On the left-hand side are the rules that we consider. So these are social choice rules which have access to ordinal preferences. And the benchmark that we will use is an omniscient algorithm that has access to these underlying hidden cardinal preferences of the voters, and it can find the optimal outcome given the cardinal preferences. So, I mean, as is well known, so this framework was introduced by Focaccia and Rosenshine in 2006, and it's known that for general utilities and costs, the comparative ratio of many voting rules is very large, but constant factor ratios are possible when we restrict the voters and the alternatives to lie in a metric space. So we will work in the metric space model. So formally, there's a set N of agents and a set S of alternatives from which we want to choose a single outcome using only ordinal information. So every agent U and every alternative A, there is a metric cost DUA or distance DUA. And the social cost of an alternative A is simply the sum of over all the voters U of the distance of U to A. So the smiley faces are the voters, the black dots are the alternatives. Given an alternative A and a voter U, there is a distance DUA. And the social cost of alternative A is simply the sum of the distances. Okay, so what is metric distortion? So let A star be the minimizer of the social cost of A. So an algorithm, a voting rule that has only access to ordinal preferences may not be able to compute A star because it doesn't have access to the distances. However, an algorithm that has access to the underlying cardinal distances can compute A star, which is the one median. So a distortion of an alternative A is simply the social cost of A over the social cost of A star. And the distortion of a social choice rule is the worst case over all input instances or all preference structures and all metric spaces that are consistent with that preference structure of the distortion of the outcome of the social choice rule. So if a social choice rule given a preference structure outputs alternative A, then we find the worst possible metric space that makes DA as large as possible. And that value of DA will be the distortion of the social choice rule. So for a randomized mechanism, the distortion of the mechanism is simply the expected distortion over the outcomes it produces. So this is standard, and I'll omit going into the details of this. So we are looking at simple social choice rules. So we can ask, okay, what is their distortion? I mean, if we rank different social choice rules by the distortion they produce, and low distortion is better, what are simple rules that have good distortion? And just to recap the questions we consider, we are looking at large outcome spaces and large numbers of voters. So what is the sample size of voters we need to bound the distortion? How many favorite or comparison queries do we need to ask per voter? And are there other queries which besides favorite and comparison that do better on this performance metric of distortion? So there's a trivial answer, which is random dictatorship, which chooses one agent at random and outputs her favorite alternative. The expected distortion is at most 3 for any metric space. And this is tight even if voters and alternatives lie on a line. In fact, random dictatorship beats any deterministic social choice rule in terms of distortion. Right? In fact, it seems to be almost best possible if our benchmark is expected distortion. This is not very satisfying. I mean, dictatorship is certainly not democracy, and this is not a social choice rule, like picking a voter at random, finding their favorite alternative and just implementing it is not what we would want. That's not how democracy works. So let's see why. So in order to understand and compare better these different social choice rules, we need to go a bit beyond distortion because we need to do a more fine-grained comparison of these rules. And for that, we need to understand, okay, what is it random dictatorship is not achieving? So one answer is squared distortion. So squared distortion is the expectation of the square of the social cost. So the formula is given here. I'm taking the square root on the outside just so that the numbers we get are comparable to distortion. So this is a different performance metric, and we can ask, okay, what can we say about squared distortion? So now we have a negative result for random dictatorship, which says that any favorite only mechanism that only asks favorite queries or top K queries has square distortion that grows with the size of the outcome space. So you won't get constant square distortion by looking at mechanisms like random dictatorship. And this suggests that we need to go beyond just asking favorite queries to bound square distortion, which is related to the variance of the distortion. Okay? So in other words, I mean, random dictatorship has good expected value of distortion, but it has huge variance around that expected value. So now this broadens our class of mechanisms that we consider. And we ask, okay, what is the smallest sample complexity we need to bound the squared distortion? So the answer is a mechanism called random referee, and this is in our AAAI paper. And we use this mechanism uses a single comparison query in addition to the favorite queries. So just draw 3 voters uniformly at random. Just ask the first 2 voters for their favorite alternatives, and now the third voter chooses the better of these 2 alternatives, and that is the output. The theorem is that the square distortion of random referee is at most 4.6. And as just using Jensen's inequality, the distortion of this mechanism is also 4.6. And the square distortion is related to the variance. So the variance of the distortion is at most 20. So the variance is a constant. So this goes beyond random dictatorship, which would have unbounded variance of the distortion. Okay. So what is the intuition? The intuition is this, that they call that A star is the minimizer of the social cost. Consider a scenario like this, where there are 2 smiley faces of voters which are close to the A star and 1 voter which is far away. Now, random dictatorship chooses a voter with the same probability. So it will choose the outlier with probability 1/3, right? Whereas random referee will only choose the outlier if 2 of the 3 agents are far away from A star. So as long as 2 of the 3 agents are close to A star, it will not output the outlier. So this concentrates the distortion better. Now we say, okay, let's try to generalize this even further. Okay? So we can define the kth moment of distortion as the expected value of the social cost of A raised to the power of K. Okay? And if the kth moment of distortion is a constant, just by using Markov's inequality, the probability that the distortion is greater than some constant C falls off roughly as C raised to minus K. Right? This means not only does the mechanism have low distortion as expectation, it also has low distortion with high probability over the randomization of the mechanism. And the high probability bound, so the tail is exponentially decaying in the parameter K. So the key question is, how many voters and alternatives do we need to make the kth moment of distortion a constant? Okay. So let's first look at the case where we consider mechanisms that have a small number of alternatives, but the number of voters could be large. Okay, so we call these mechanisms of type all. So the idea is, so the first step is to elicit the favorite alternative of S voters chosen at random, where S is a parameter. Put these alternatives, once we have these alternatives, just get all the voters together and put these alternatives to a vote. Now aggregate these votes using some social choice rule X. Okay. So the first lower bounding theorem is that if you want the kth moment of distortion to be a constant, we need to elicit the favorite alternative of at least S voters. So you need to have at least S alternatives to get the kth moment to be a constant. And now suppose we define this concrete mechanism PRCS, where in the third step, in order to aggregate all the votes, we just use the Copeland rule. And the theorem is that if you run this PRC mechanism where you sample K voters in the first step, it has kth moment of distortion, a constant, which is at most 11. This constant can probably be improved. We haven't like completely tightened it, but it's a small constant. Right? So this shows that a necessary and sufficient condition for this kind of mechanism to have constant kth moment of distortion is to choose K voters at random and ask them for their favorite alternatives and put all these alternatives to vote, aggregate them using some low distortion rule like Copeland. Okay. So the previous mechanism, the number of voters is large. So you have a small number of alternatives, but then you're putting these to vote among all the voters. Okay. What if you want a few voters as well? So this leads to a class of mechanism, let's call it sum. So you elicit the favorite alternatives of S voters at random, put these alternatives to vote just among these S voters. So these S voters both produce their favorite alternatives and then rank everybody else's alternatives, and then aggregate these using some rule X. And the theorem, the lower bounding theorem is that you need at least 2k minus 1 voters to make a mechanism of this type have constant kth moment of distortion. Right? And again, define a mechanism FRCS where the rule that you use to aggregate all the votes is just the Copeland rule. And now if you run the Copeland rule using 2k minus 1 voters, then it has constant kth moment of distortion. This constant is 17. Again, it can potentially be tightened. Right? So this shows that, so this gives us a tight characterization of what we can do when you're given a small number of voters and alternatives. So the kth moment of distortion gives us a fine-grained way of saying, okay, what exactly is improving as I give you more and more voters and alternatives. So we actually did some empirical simulation. So we took knapsack voting data. So the voter's favorite alternative is just the knapsack vote. And we put a metric distance, which is say the Jacquard distance between the votes. Right? And then we simulated this FRC and PRC mechanisms, which only use ordinal information, but to measure distortion, we impose this Jacquard distance. And then we plot the distribution of the distortion, and we see that this becomes more and more concentrated as you increase the value of K for both PRC and FRC. Okay, so in the last part of the talk, we'll discuss going beyond this voting, participatory budgeting kind of setting and into settings where we want to model compromise and coming up with new alternatives, where people discuss stuff with each other and they come up with new alternatives. Right? A concrete way to model this is to say that, I mean, different agents may have different favorite points or bliss points, but the actual social optimum may not be anybody's bliss point, and it may not be in your initial list of alternatives. Right? And so the idea to find such a solution is to make people talk with each other and make them compromise. Right? And in this part, I'm assuming that the voters are located at their bliss points just to make our analysis simpler. Right? So if these black points represent the voters and their bliss points, the social optimum might be this star, the green star. So the idea to make people compromise is to take the left two black voters, the black dots, which are the voters, make them talk with each other. Maybe they find a blue alternative, the left blue alternative. Now take the right two voters, they find the right blue alternative. right? And now if you like get other voters to consider these blue alternatives, maybe they'll find the optimum alternative. So the concrete protocol we have is called sequential deliberation. So here X1 is the favorite alternative of a random agent. And for T steps, we do the following process. You choose two random agents, IT and JT, make them talk to each other or bargain using XT, which is your previous outcome, as the no compromise outcome. You tell IT and JT, you talk with each other. So far, the best alternative found is XT. If you guys can't agree on how to improve XT, then XT will be the alternative that goes to the next phase. Right? So XT plus 1 will be the outcome of the bargaining process or the compromise process between IT and JT. So you run this for capital T steps and finally output the X capital T. So in particular, if you, one step of deliberation can be modeled as IT and JT are given this outcome from the previous step XT, and they are told that, okay, bargain to improve this outcome. If you can't agree, then XT will be the outcome that goes to the next phase. And if IT and JT bargain, they might find an alternative XT plus 1, which is better than XT for both of them. So in order to analyze such a process, we consider a restricted metric space called median graphs. The definition is not super important. It just says that for any triple of vertices, there is a unique common point on the pairwise shortest paths. And this unique common point is a median of X, Y, and Z. So examples of median graphs are trees, hypercubes, and grids. And in these graphs, if you run a social choice rule, it has a, like the preference profiles have a Condorcet winner. Whereas things that are not median graphs are, say, odd cycles or disconnected graphs. So the specific kind of bargaining that we assume that happens between two agents is Nash bargaining. And there's a theorem due to Nash which says that, this Nash, the solution to the bargaining problem on two agents is an outcome that maximizes the Nash product. The details are not important, but on median graphs, we can show that Nash bargaining outputs the median of IT, JT, and XT. So if IT and JT are the two agents, and XT is the outside alternative or the disagreement alternative, and suppose we put a median graph, which is a grid graph, then if they bargain, the Nash bargaining solution outputs XT plus 1, which is the median of IT, JT, and XT on the grid graph. Okay, so the sequential deliberation problem protocol is simply that you start with the favorite or bliss point of a random agent. For T steps, choose two random agents, make them bargain using the previous outcome as the no compromise outcome. And the outcome that they find will be the median of their bliss points, and there's no compromise outcome. That is fed to the next stage. You repeat this for T steps and output, finally output the final outcome. Okay, so what are the conclusions we can draw? The first conclusion we can draw is that in median graphs, if you look at, if the metric of performance metric is distortion, then bargaining or like any bargaining process is better than using only bliss points. So if you just use the bliss points of the voters and put them to vote anyhow you felt like, the distortion is at least 2. Whereas if you did sequential deliberation, the distortion is 1.208. So the compromise solutions that are found provably improve distortion, regardless of what you did just using the bliss points. The second qualitative conclusion is that many rounds of deliberation are better than just one round of deliberation. If you just did one round of deliberation, it would output the median of 3 bliss points. But such a mechanism would have distortion at least 1.316. And if you did it for many rounds, you get 1.208, which is better. And finally, any mechanism that where the outcome lies on the shortest paths between bliss points has distortion at least 1.125. I mean, we are comparing against a social optimum, which could lie anywhere in the median graph. I mean, there is, we don't have much control over that. The protocols that we run are finding medians of 3 points. So they will lie on the shortest path between some 2 bliss points. Right? And what we can show is that any such mechanism has distortion at least 1.125. Our mechanism has distortion 1.208, which is not much worse than 1.125. Right? So this shows that on median graphs, our protocol provably improves distortion compared to just using bliss points. And in a sense, this gives some quantitative insight into why making people talk with each other is useful. So that is the end of the technical part of my talk, where we looked at low complexity social choice mechanisms and what are measures that we can use to analyze these kind of mechanisms. So there are several open questions. So firstly, are there other practical primitives for low complexity social choice? I mean, can we, for example, model multi-agent bargaining? This gets very tricky. Two-agent bargaining has this nice characterization due to Nash and Rubinstein and so on. Multi-agent bargaining, the characterizations become very messy. If we, like, analogous to the kth moment of distortion, are there performance metrics we can impose as we increase the number of agents who participate in deliberation, right? And our restriction to median graphs is nice, but can our results extend beyond median graphs? A second natural question is that if we are considering mechanisms with small numbers of voters and small numbers of alternatives, how do we know if we have covered the entire space of alternatives? How do we know that we are not missing something important, right? And this is related to this problem called good Turing estimation in statistics. It's unclear, like we need like some kind of good statistical way of saying that, okay, what, like given an actual voting rule that has been implemented in a city, or the outcome that it finds or the policy that it finds did not miss something super important. Finally, I mean, we have been considering mechanisms that find one winner or one outcome. How do we generalize it to finding multiple winners? And this is not super straightforward. Sampling to find k-medians, for example, is not as straightforward as sampling to find the one median. So that is the end of my talk. Thank you.